Good morning, everyone. Today we're going to talk about one of the most influential ideas in modern artificial intelligence, neural networks. If you've used a smartphone assistant, interacted with a chatbot, unlocked your phone with facial recognition, or even received a personalized recommendation online, you've already experienced the impact of neural networks. They are no longer experimental research tools. They are foundational technologies that power many of the systems shaping our digital world. But despite their widespread use, neural networks are often misunderstood. Some people see them as mysterious black boxes. Others see them as magical solutions that can solve any problem. Neither view is entirely accurate. In this session, we're going to break them down clearly and conceptually. We'll start by understanding their purpose, what they are actually designed to do. Then we'll explore the intuition behind how they work, without getting lost in heavy mathematics. After that, we'll look at real-world applications to see where they are making an impact today. And finally, we'll evaluate their strengths and limitations so that you can make informed decisions about when and how to use them. By the end of this presentation, you should not only understand how neural networks function, but also develop the judgment to decide when they are the right tool for a problem and when they are not. Because understanding a model is one thing, knowing when to apply it responsibly and strategically is what makes you a thoughtful AI practitioner. Let's begin. When we talk about neural networks, it's easy to jump straight into technical diagrams and equations. But before we do that, I want us to step back and ask a simpler question. What is a neural network actually trying to do? At its core, a neural network exists to learn patterns from data. That's it. It is not memorizing facts the way a database does, and it is not following rigid rules that a human explicitly programs into it. Instead, it is trying to discover structure. It is trying to detect relationships between inputs and outputs that are not immediately obvious. More specifically, a neural network attempts to approximate an unknown function. Imagine there is some hidden rule that maps inputs to outputs. We don't know the rule, we don't write the rule, but we provide examples. The network studies those examples and gradually adjusts itself until it becomes a very good approximation of that hidden mapping. In doing so, it can model nonlinear relationships that cannot be captured by simple straight lines or basic formulas. That is the purpose. Now, let's talk about the intuition behind how this works. Neural networks are loosely inspired by biological neurons, not in a literal biological sense, but conceptually. Think of many small computational units connected together. Each unit performs a simple transformation. On its own, each unit is limited and not very impressive. But when you connect thousands or even millions of these units together in layers, something powerful emerges. Each neuron receives information, applies a transformation, and passes the result forward. The next layer does the same thing, and then the next. Over time, as information flows through these layers, it is gradually transformed into more abstract representations. For example, in an image recognition task, the first layer might detect simple patterns like edges or lines. The next layer might combine those into shapes. Later layers might detect parts of objects. Eventually, the network can represent something complex like a face or a car. The key idea is that each layer builds on the previous one, creating increasingly rich internal representations. This layered transformation process is central to deep learning. However, neural networks operate under important assumptions. First, they assume that the data contains learnable patterns. If the world were completely random, there would be nothing to extract and nothing to approximate. Neural networks work because reality has structure. Images have patterns, language has patterns, human behavior has patterns, Second, neural networks generally assume access to sufficient data. These models tend to perform better as the amount of high-quality representative data increases. They are powerful, but they are data dependent. Without enough examples, they struggle to generalize. Third, they assume that complex relationships can be captured through layered transformations. This is a powerful assumption. It means that instead of solving a problem in one step, the model can build complexity gradually. Simple features become intermediate features. Intermediate features become high-level representations. Step by step, layer by layer, complexity emerges. There is even a theoretical concept, often referred to as universal approximation. Conceptually, it suggests that a sufficiently large neural network can approximate almost any function. That does not mean training is trivial or guaranteed to succeed, but it highlights the expressive power of these models. So when we talk about neural networks, we are really talking about systems designed to learn representations from data by stacking simple transformations into deep structures. They are powerful because they can model nonlinear relationships. They are flexible because they can approximate complex mappings. And they are effective because the world itself contains patterns that can be learned. Understanding their purpose, intuition, and assumptions helps us see them not as mysterious black boxes, but as structured learning systems grounded in mathematical principles and real-world regularities. And once you understand that, neural networks stop feeling magical and start feeling logical. Now that we understand the purpose and intuition behind neural networks, let's talk about how they actually make a prediction conceptually. Every prediction begins at the input layer. This is where raw features enter the network. If we're working with images, those features are pixel values. If we're working with text, they are numerical representations of words. And if we're predicting something like housing prices, the inputs might include square footage, location, or number of bedrooms. At this stage, the network doesn't understand meaning the way we do. It simply receives numbers. From there, the information flows into the hidden layers. And this is where the transformation begins. Each neuron performs two essential operations. First, it computes a weighted combination of its inputs, effectively learning which signals matter more. Second, it applies a nonlinear activation function. That nonlinearity is crucial because without it, the network would behave like a simple linear model. As information passes through multiple hidden layers, the representation becomes increasingly abstract. In image recognition, early layers may detect edges or color gradients. Later layers may combine those edges into shapes. Deeper layers may recognize parts of objects. And eventually, the network constructs a high-level internal representation that supports a final decision. Finally, the information reaches the output layer. If the task is classification, the output may represent probabilities across categories. If it's regression, the output may be a continuous numerical value. The structure remains the same. Input enters, hidden layers transform, and the output layer produces a prediction. The key idea is that each layer extracts more abstract features than the one before it. Instead of solving the problem in one step, the network builds complexity gradually. And when you see it that way, neural network prediction stops feeling mysterious. It becomes a structured process of layer transformation, turning raw numbers into meaningful outputs. Now that we understand how neural networks work conceptually, the next logical question is this: where do we actually see them in the real world? And the answer is almost everywhere. One of the most visible areas is computer vision. Whenever a system can interpret and understand images or video, there's almost always a neural network behind it. Object detection systems, for example, allow software to identify and locate multiple objects within an image. That's how modern cameras can automatically focus on faces, and how surveillance systems can track movement. Facial recognition is another well-known application. Neural networks analyze subtle patterns in facial structure and map them into mathematical representations that can distinguish one individual from another. It's not comparing pictures pixel by pixel. It's comparing learned feature representations. Autonomous vehicles rely heavily on neural networks as well. A self-driving system must interpret traffic signs, detect pedestrians, recognize lane markings, and respond to dynamic environments, all in real time. That level of perception requires layered feature extraction and fast prediction. Medical imaging is another powerful example. Neural networks assist radiologists by detecting anomalies in X-rays, MREs, and CT scans. They don't replace physicians, but they can help highlight patterns that may be difficult to detect with the naked eye. Now, let's shift to natural language processing. When machines understand and generate human language, neural networks are at the core of that capability. Chatbots are perhaps the most familiar example. They analyze text input, interpret meaning, and generate contextually appropriate responses. Modern systems rely on deep neural architectures that learn patterns across enormous text datasets. Language translation systems also use neural networks. Instead of translating word by word, they learn contextual representations of entire sentences. That's why modern translation tools sound significantly more natural than earlier rule-based systems. Sentiment analysis is another application. Companies analyze customer reviews, social media posts, and feedback to determine whether opinions are positive, negative, or neutral. Neural networks learn to detect subtle linguistic patterns that signal emotion or tone. Speech recognition takes this one step further. When you speak to a virtual assistant and it converts your voice into text, a neural network is processing acoustic patterns and mapping them into language representations. Across all of these domains, vision, language, audio, and decision making, the common thread is representation learning. Neural networks excel at transforming raw, high-dimensional data into structured internal representations that support prediction, and that's why they dominate modern AI applications. They are particularly effective when the data is complex, unstructured, and nonlinear, like images, text, and sound. So when we talk about neural networks, we're not talking about abstract academic models. We're talking about the engines behind technologies you interact with every single day. And that real-world impact is what makes understanding them so important. Now that we've seen how neural networks work and where they're used, it's important to take a balanced view. These models are powerful, but they are not perfect. Understanding both their strengths and their limitations is what allows us to use them responsibly and effectively. Let's start with the strengths. One of the most significant advantages of neural networks is their ability to handle nonlinear relationships. Many real-world problems are not simple or linear. The relationship between variables can be complex, layered, and interactive. Neural networks, because of their nonlinear activation functions and layered structure, can capture those complexities in ways that traditional linear models cannot. Another major strength is automatic feature learning. In many classical machine learning approaches, a human must carefully design features before training the model. That process can be time-consuming and requires deep domain expertise. Neural networks, particularly deep networks, learn intermediate representations on their own. They discover which patterns are useful and which are not, reducing the need for manual feature engineering. They also tend to achieve high accuracy on complex tasks, especially when large data sets are available. In areas like image recognition, speech processing, and natural language understanding, deep neural networks have surpassed older approaches by significant margins. And importantly, they scale well with large amounts of data. As datasets grow, neural networks often continue to improve, whereas simpler models may plateau in performance. But with those strengths come meaningful limitations. First, neural networks typically require large datasets. While there are techniques like transfer learning and data augmentation that can help, these models generally perform best when trained on substantial amounts of high-quality data. Without enough data, they can struggle to generalize effectively. Second, they are computationally expensive. Training deep neural networks can require significant hardware resources, including GPUs or specialized accelerators. That has implications for cost, energy consumption, and accessibility. Another limitation is interpretability. Neural networks are often described as black boxes because it can be difficult to clearly explain why a specific prediction was made. While there are methods for model interpretability, the internal representations learned by deep networks are not always intuitive or easily translated into simple rules. There is also the risk of overfitting. Because neural networks are highly expressive, they can sometimes learn noise in the training data rather than true underlying patterns. Careful validation, regularization, and model tuning are necessary to mitigate that risk. Finally, they are sensitive to hyperparameters. Choices such as learning rate, network depth, architecture, and regularization strategies can significantly influence performance. Tuning these parameters often requires experimentation and experience. So the takeaway is not that neural networks are inherently superior to all other models. Instead, they are powerful tools that are particularly well suited for certain types of problems, especially those involving high-dimensional, unstructured data. The key is understanding when their strengths align with the problem you're trying to solve, and when a simpler, more interpretable model might actually be the better choice. And that balance, knowing both capability and constraint, is what separates using neural networks from truly understanding them. Now that we've explored what neural networks are, how they work, where they are used, and what their strengths and limitations are, we arrive at a practical question. When should you actually use one? Neural networks are not automatically the right answer to every problem. They are powerful tools, but like any tool, they are most effective under the right conditions. You should consider using a neural network when your data set is large and rich. These models thrive on data. The more examples they see, the better they can refine their internal representations and generalize to new cases. They are also a strong choice when the relationships in your data are nonlinear. If the patterns are complex and cannot be captured by simple straight line boundaries, neural networks provide the flexibility needed to model that complexity. Another situation where they shine is when feature engineering is difficult. In domains like image processing, audio analysis, or natural language understanding, manually designing features can be extremely challenging. Neural networks can learn intermediate representations automatically, reducing the need for handcrafted rules. And sometimes accuracy is the primary objective. In certain applications, achieving the highest predicted performance may matter more than having a fully interpretable model. In those cases, a neural network can be an appropriate choice. However, there are situations where you should avoid them. If your data set is small, a neural network may not be the best option. Simpler models often generalize better in low data environments. If interpretability is required, for example, is in regulated industries where decisions must be clearly explained, then a more transparent model may be preferable. And if the problem is linearly separable, meaning a simple boundary can effectively separate the classes, then using a deep neural network would likely be unnecessary complexity. The key takeaway is this: neural networks are not a default solution. They are a strategic choice. As machine learning practitioners, our responsibility is not just to know how to build complex models, but to know when complexity is justified. Sometimes the most intelligent decision is choosing a simpler model, and sometimes the complexity of the problem truly demands a deeper architecture. Understanding that distinction is what transforms someone from a model user into a thoughtful AI practitioner, and that ultimately is the goal.